Hello, my name is Jacob Krantz and I am a PhD student at Oregon State University. I will be introducing the Room Across Room Habitat Challenge, hosted at this year's Embodied AI workshop. I will present the task, results, and share what we learned about this difficult language-guided navigation task. In the RxR-Habitat Challenge, an agent is placed in a previously unseen, simulated environment with the goal of accomplishing a vision and language navigation task. The agent is given a natural language instruction, such as, take a left and go down the hallway, turn into the bedroom on the left, and stop at the foot of the bed. This instruction describes a path through the environment, which necessitates grounding language in the visual scene and reasoning jointly about vision and language. The agent then must follow this path, given a discrete action space of left, forward, right, and stop actions. We also allow the agent to manipulate the camera with look up and look down actions. Contributing to the difficulty of this task is that the agent must operate from ecocentric vision alone. At every time step, the agent receives a forward-facing RGB and depth frame. Active perception is required for the agent to gain information about the environment. We instantiate the agent in a 3D scene reconstruction from the Matterport 3D dataset. These reconstructions provide unconstrained agent navigation that reflect the continuous nature of navigating in the real world. Such realistic difficulties include colliding with objects, getting stuck in tight areas, and visual occlusion. We run these simulations with the Habitat Simulator, which also powers 3 other challenges at the Embodied AI workshop. The dataset for our challenge is the Room Across Room dataset, or RxR for short. RxR is a recently released vision and language navigation dataset with instruction path pairs spanning 60 scenes in the Matterport dataset. RxR has many characteristics that make it compelling for both the training and evaluation of instruction following agents. It contains 16,500 navigation paths, supporting 126,000 instructions over 3 different languages. The dataset also contains time-aligned pose traces that detail when and where the annotator was looking while giving the instruction. In comparing RxR to an existing popular VLN dataset, the room-to-room dataset, we see that RxR has an order of magnitude more paths, is multilingual instead of monolingual, and removes the shortest path prior of room-to-room. The shortest path prior is the understanding that every path in room-to-room travels the shortest distance between start and goal locations, like in this example. However, room across room samples more challenging paths, as shown here. As you can see in the last diagram, RxR was created within navigation graph environments. This means that agents navigate by teleporting between adjacent nodes. To make the RxR dataset compatible with continuous 3D environments, we follow the conversion process for vision and language navigation in continuous environments. This includes porting all nodes in the navigation graph to positions in the reconstructed navigation mesh, pruning episodes with nodes that cannot transfer, and pruning episodes that an Oracle agent cannot successfully navigate. This yields the converted RxR-Habitat dataset, complete with its own test challenge split, accessible only through the leaderboard. The RxR-Habitat dataset is now the largest VLN dataset for continuous environments, with nearly 90,000 instructions. For the simulated embodiment of this agent, we synchronized with the Habitat Object Nav Challenge and modeled the agent after a zero-turn radius LocalBot robot with an Intel RealSense camera. Some of the relevant configurations are shown here, such as the agent's height and radius, the camera's horizontal field of view, and collision sliding. When sliding is enabled, actions resulting in collision make the agent slide along the wall or object for some distance. Disabling this video game-like simulation feature makes collision avoidance more important. To evaluate agents in the RxR-Habitat Challenge, we choose the primary metric to be normalized dynamic time warping, or NDTW. This metric computes the path alignment between an agent's path, labeled Q, and an Oracle ground truth path, labeled R. An ideal agent would maximize the expected NDTW across all episodes with a score of 1.0, indicating perfect path alignment. We use NDTW as the primary metric because RxR does not have a shortest path prior. We care more about an agent's ability to follow a path than its ability to reach the specific endpoint of a path. we include a suite of secondary metrics, both success-based, including SR, SPL, and SDTW, and descriptive, such as path length. To establish baseline performance on the RxR-Habitat task, we train a pre-existing cross-modal attention model based on the reinforced cross-modal matching model in VLN. We feed this model pre-computed BERT instruction embeddings provided in RxR. The model itself uses single-modality encoders, tracks visual history with a GRU, uses the visual hidden state to attend to instruction features, uses the attended instruction features to then attend to spatial attention, and finally passes through a second GRU to predict an action. We use teacher forcing to train this model, which learns to clone the behavior of the oracle. We train our model on monolingual episodes, which leads to having one model per language. For evaluation, we merge the predictions into a single submission. We submitted this model to the leaderboard back in March. It earned an NDTW near 31 and a success rate near 14. The official submission window closed at the end of May. We had several teams participate in the challenge and work hard at developing new models. However, the baseline model proved hard to beat. As such, the leaderboard received one official submission. The team named Player 1 submitted their model Zorro, which was multilingual by training and evaluating on all languages jointly. Zorro involved separate RGB and depth language attentions. It was trained with a progress monitor loss and a scaled stop action loss. Here we look into the performance of the baseline model on the unseen validation split. We find that performance across languages is similar, with a range of less than 2 NDTW. We also run an evaluation with sliding turned on. While sliding increases performance, the magnitude is not substantial. As a community, we have a long way to go on this task. Looking forward, we can work on generalizing ideas in VLN to continuous environments and mitigating the computational cost of current methods. I would like to thank everyone who participated in the challenge, my fellow challenge organizers, and all the organizers at the Embodied AI workshop. While the official challenge is over, the leaderboard remains open. I encourage you to bring clever new ideas, check out the starter code, and compete on the leaderboard for the top spot in this difficult task. Thank you.